basically just disregard, I mean, that. But neither of the other ones can do it. Basically, yeah. Basically. Exactly, yes. I mean, so. Yes, absolutely. That's exactly.
All right, let's start. Oh, one sec. Can you hear me in the back? Let me just make it louder. Okay. All right, so we're moving on. So today we're going to talk about lipids. So this would be like the fourth major class of molecules in the biological systems, like polymeric molecules. And this is chapter 10 in linear principles of biochemistry. So if you would ask me to give a strict definition of what the lipids are, I'm afraid I will fail to do so. So if I would ask you to give a strict definition of amino acids, which makes proteins, or nucleotides, or even sugars, I mean, you will be able to do it, right? So with amino acids, I mean, we clearly know what the formula is. I mean, we cannot define the formula, the like general formula for sugars, but we know that since they're called carbohydrates, I mean, they have equal number of carbons and sort of waters. And nucleotides, we know what they're made of: nucleobases, ribose, or deoxyribose, and phosphates. In the case of lipids, I mean, we cannot give a definition because this is just a group of structurally very diverse, structurally and chemically very diverse organic molecules. And the only thing that sort of groups them or brings them together, it's the low solubility in water. So, and the good solubility in non-polar solvents. And the fact that they are relatively hydrophobic. So I'm not sure how you're familiar with these terms, hydrophobic, hydrophilic, but it's like basically originates from the Greek words like phobia or philia, so meaning liking or disliking. So phobic means not liking. So hydrophobic means not liking the water. So these are the molecules that tend not to mix up with water and not to dissolve in water. So all of you know what will happen if you spill oil in the water. It will not be mixed up with water. It will be sort of aggregating in blobs together. Okay. So what I'm showing you, just structurally very diverse molecules. So there could be fatty acids. There could be steroids. So we'll also talk about like triacylglycerols and the different pigments. Okay. So first of all, what are the main biological functions of lipids? One of the major, most important function of the lipids in biological systems is the membrane structure and integrity. So they're predominant structural components of the cellular membranes. And we're not going to talk much about this today because we'll dedicate a whole lecture next time, like this Thursday, about the biological membranes. And for now, we just take it for granted that biological membranes are made of lipids. So another very important function is the storage of energy. So these are reduced compounds, and as a result, they have lots of available energy. So what does mean reduced? They have less oxygens compared, for example, to sugars, right? So sugars are more oxidized compounds, so they have less energy than lipids. And they have, because of their hydrophobic nature, so there is no need to use water for packing, so that you can just sort of store them in one place inside the animal, for example, right? And you won't need much water for that. Another important function, but it's not like generally applicable to all living organisms, only in the particular cases, it's insulation from the environment. So both thermal and mechanical. So for example, due to their low thermal conductivity and high heat capacity, so lipids are ideal materials for this kind of thermo shields. So also, of course, the lipids can be used as water repellents. And again, so their hydrophobic nature helps a lot. So in the particular animals, they can participate in the buoyancy control, such as like whales, for example. Quite often, some lipids participate in the enzymatic reactions as cofactors. So like coenzyme Q, for example, or vitamin K. So these are the most famous ones. Also, they can be antioxidants or even pigments. So, finally, many signaling molecules belong to the class of lipids. Perhaps the most famous here would be steroid hormones. So, okay. What is the classification of lipids? Of course, just as with sugars or with nucleotides, there are many different approaches or ways how we can classify them. The simplest one is based on the structure and function. So here we have basically two classes: non-fatty acid containing lipids and fatty acid containing lipids. So in the fatty acid containing lipids, we will have storage lipids and membrane lipids. So we will first talk about the fatty acid containing lipids because they're the simplest one from a chemical point of view. So in the storage lipids, here in the classification is basically just this little group on the left-hand side. So pretty much it's represented by triacylglycerols. Okay. So the name comes from the fact that chemically it's just esters of the glycerol, which is a triatomic alcohol with 3 fatty acids. But before we'll talk about triacylglycerols, let's talk about the fatty acids themselves. Another basically here just to show you that how the energy storage can occur. This is just the basically fat inside the cells, and what is the membrane structure. So membranes are made out of the phospholipids that make the bilayer. So we'll talk in detail later. Okay, fatty acids. So fatty acids are carboxylic acids with hydrocarbon chains containing between 4 to 36 carbons. So what are the simplest carboxylic acids that you know, that you remember from organic chemistry course? The simplest. Acetic acid, yes. What would be the one below acetic acid? Formic acid, yes. So formic acid, acetic acid, then propionic acid, then butyric acid. So we don't call these ones fatty acids because they're too short. So, but starting approximately from, like here it says 4, that's a butyric acid, but even butyric acid is not really a fatty acid. So once the solubility in water drops significantly, like they become almost non-soluble, that is when actually we start calling them the fatty acids. So essentially the chemical formulas are shown at the bottom here. So this is conceptually, it's not any different from acetic acid. It just, the hydrocarbon chain is just longer. So it's a hydrocarbon chain plus a COOH group at the end. So which is which defined what the carbonic acid is. So almost all naturally occurring fatty acids have an even number of carbons. So all of them have, let's say, 16, 18, or 20 carbons, but not 17 or 15, for example. And you will see in this course we are not talking about like why is that, but in reality it's like when they're synthesized. So the acetyl coenzyme A segments are used, which carry 2 carbon atoms, and when they actually sort of added together, so they added in the increment of 2. So that is the reason why all biologically occurring fatty acids have the even number of carbons. So they can have various saturation levels. So this is very important. So they could be fully saturated, so there is no double bonds. So they could be monounsaturated or polyunsaturated. In this case, they have 1 or 2 double bonds. So see, that's shown here. What is important is that double bonds of the polyunsaturated fatty acids are almost never conjugated. So conjugated means that they separated by basically that their pi electron clouds actually can interact with each other. As a result, there would be a resonance structure. They always have a CH2 in between. So as a result, so this double bonds, if they occur in the fatty acids, so they never can never form resonance structures. And also it's important so that these double bonds are naturally always in the cis configuration. So which means that the molecule would look like that. It would be kind of bent. So at the point where the double bond occurred. So as opposed to trans, which I'll show you in the next couple slides. Okay, what is the nomenclature? So chain length and the number of double bonds are separated by a colon. So which is basically we write, for example, in the case of this stearic acid, so we basically say 18 colon 1, which means that the 18 carbons and the 1 double bond. So and then in the brackets we put like delta 9. So that's a position at which the double bond is located. For the polyunsaturated fatty acids, polyunsaturated means like having multiple double bonds. So the alternative nomenclature can be used where the location of double bonds is basically denoted relative to its terminal end. So the terminal, oops, my laser pointer is not working anymore. So the terminal end is denoted as omega, right? So then like the first atom at which the double bond is located would be omega 3, 6, 9, and so on. Perhaps, this name should probably ring a bell, right? So when you walk in the pharmacy and see those fish oil capsules, they say, oh, rich in omega 3 and 6. And more expensive would be rich in 3, 6, and 9. And the most expensive would be 3, 6, 9, and 12. So these are the fatty acids, basically, which contains this polyunsaturated, basically polyunsaturated fatty acids. So they have multiple double bonds. Okay. Here's just a table, summarizing basically the most common fatty acids in the living nature. And the most important, which I would like you to pay attention to, is just this palmitic, stearic, so which are 16 and 18. So these are fully saturated, so no double bonds. Again, I'm not going to be asking you to draw the formula of this because it's kind of too simple. Because, if you know that they have 16 and 18, right, so you know that they're 16 carbons all saturated, and then you would have COH at the end. So, and there's actually two more important acids from the unsaturated group. So this would be the palmate oleic and oleic acids. Again, these four, the palmitic, stearic, palmate oleic, and oleic acids are the most common ones in the cells. So, and they exist in multiple places in the cell, as we will see, depending on the function of the lipid. Okay. Very important consideration when talking about lipids is the melting point of fatty acids. So physical properties of fatty acids are largely determined by their length and degree of unsaturation. So, typically they're very poorly soluble in water. So, and the solubility in water decreases as the chain length increases. Basically, if we go back to the stable, right? So the solubility in water, you can see it here, will go down as the chain length will be increasing and increasing and increasing. So, melting point. So saturated fatty acids from 12 to 24 carbons long have solid waxy consistency. Basically, it's like, treated as, like, for example, a butter. Like, you know butter, how butter looks like, right? So this is a saturated fatty acids. So it's solid. So, but as the double bonds are being introduced into the fatty acids, they become liquid. So the unsaturated fatty acids of the same length are oily liquids. And so the melting point, which is the temperature, at which the solid fatty acid turns into liquid, so increases as the chain length increases and decreases as the number of double bond increases. So what that means, so if you basically have the same length fatty acid, once you introduced the, let's say if it's saturated, it was solid, but once you introduced the double bond, it became liquid. So we'll talk more about this in a second. Well, first of all, why this happens? The saturated chain tends to adopt an extended conformation like this. And the double bond in natural unsaturated fatty acid are commonly in cis configuration, as I already mentioned. So, and this causes a kink. So, again, the saturated ones are straight, so the unsaturated are kinked. I usually like to explain it by the following analogy, like why it's happening. So, treat it as the bunch of straws. Like, you know, the straws that you can buy right now, so they have like a little bending point at the top, right? So like now, the moment when you took them out of the pack, so they're all parallel. So these would be the saturated fatty acids. As a result, they pack densely and nicely against each other, and that's what makes them solid. So they have lots of intermolecular interactions, and that's what keep this, the consistency of such compounds solid. So, but once you introduce the double bond, it kind of kinked them. So the same as what you will take those straws and sort of start bending them. So it will be something like what is shown here. As a result, there's way less number of intermolecular interactions between the molecules in this case, which results in them in liquidish consistency of the resulting compound. So summary. Okay. So fatty acids by themselves are not usually present in high concentrations or high amounts in the cells or in the organisms. So they're usually present in the form of triacyl glycerols. And here we can actually have two different types of them, fats and oils. So as you can guess from the name, fats are solid, oils are liquids. So simplest lipids constructed from fatty acids. So, and basically just a result of esterification of a glycerol with free fatty acid molecules. So, and unlike fatty acids themselves, again, if we go back here, remember that the fatty acid is a polar molecule. Although it has a long hydrophobic tail, right, at the top, at one end, there is a carboxyl group, which is not only which is not only polar, but it's even charged. It has a negative charge. So, and when you esterify these molecules to the glycerol, right? So you will actually get a non-polar molecule. So, or no, like without a charge group. So the name triacylglycerol basically kind of says it all. So that the glycerol is esterified in the 3 positions. So that the free OHs are involved in the ester bond, in the ester linkages with free fatty acids. So, so majority of the fatty acids in biological systems are found in the form of triacylglycerols. So, and if the triacylglycerol is solid, it's called fat. If it's liquid, it's called oil. So, and the main function of triacylglycerols is storage of energy, basically. So, okay. So, different mixtures of triacylglycerols have different melting points, and therefore different physical properties at room temperature. So, for example, I mean here just the figure from the textbook, which shows you the composition of different like common types of oils and fats. I mean that we can find. Like for example, butter. So it's a soft solid which have a relatively large proportion of saturated fatty acids. Again, it's made of triacylglycerols, right? But triacylglycerols themselves are made of the fatty acids. And the butter would have a high proportion of the saturated, but also will have a lot of unsaturated fatty acids. So the much more solid fat, such as beef fat, for example, have a high proportion of the saturated fatty acids, and as a result, it will be more solid. On the other hand, the olive oil, so which we know is a liquid, right, has a really high proportion of the unsaturated fatty acid chains. So, actually, a good olive oil would have relatively small proportion of these saturated fatty acids. You can easily check this. I mean, whether the olive oil is like really good, expensive one. If you will put it at 4 degrees in the regular refrigerator, I mean, it will not turn cloudy. So, because I mean this saturated fatty triacylglycerols made of the saturated fatty acid will precipitate. They will turn solid at a low temperature. And actually, if there would be very little of them, so then the olive oil will not turn cloudy. So that's an easy test, I mean, for the quality. Okay. When we were talking about the polysaccharides, so we also were talking that they use such polysaccharides such as starch or glycogen are used as basically fuel storage. So. And now we're talking about fats, I mean, which also been fuel storage. So advantages of fat over the polysaccharides as storage materials. So the fatty acids carry more energy per carbon because they're more reduced. So and fatty acids carry less water, so per gram of mass because they're non-polar. So the water, they don't really need water. While the glycogen or starch needs the water to be around them. So you can treat this as basically, like for example, if you, I don't know, probably none of you lives like in remote places where there is like outage of electricity can occur quite often. But those people who live in the houses far away, they usually have the generator, like a diesel or something like that. Okay, so if the power energy occurs, so then the flashlight, which has like a, I mean, sort of battery-powered flashlight, would be an analogy to sugars, right? So it's very quick to grab, very quick to extract energy, very quick to use the light, right? While the diesel generator takes some time to actually start it, connect it, I mean, so to, and this would be an analogy of, like lipids or fats. So in other words, so sugars, I mean, can be used quickly, and the energy can be extracted quickly, but they cannot last for a long time, so they short-lived. So on the other hand, the fats, I mean, they contain much more energy, just like a diesel generator has a large tank, and as long as the tank lasts, I mean, so you will have this power. So the same thing. So the organism need this sort of plasticity. So they need to, at times, they need to extract energy quickly. So, and also they would need to have a prolonged sources of energy, like such as fats. That's why we need like both types of fuels available. Okay. So what, perhaps you heard about the trans fatty acids. So like in the previous slide, one of the previous slides, I showed you that most of the double bonds that naturally occur in the fatty acids are cis double bonds. And we get used to hear in mass media about the trans fatty acids. So trans fatty acids form during partial hydrogenation of unsaturated fatty acids as an unwanted byproduct. You may ask, why do we even need to like do this hydrogenation? In the food industry, it's very easy to obtain liquid oils, right? So from plants. So it's cheap and easy. But the shelf life of those oils is relatively short. I mean, so they do not last for a long time. And to preserve them, the simple way of preserving those basically sources of energy is to hydrogenate them. So what will happen during again, because they're liquid oils, obviously they have some number of double bonds, right? So, double bonds means that they're unsaturated. So during hydrogenation, those bonds will be reduced, right? So meaning that they will turn into the stretched, saturated fatty acids. And that will turn them solid, so that those oils, like for example margarine, right, that you can buy in the store, it looks the same as like regular butter, but it's actually made of its source is different. So it's made out of the plant oil that was hydrogenated, as a result turned solid. So when during this process, because again it's a completely chemical hydrogenation, I mean this industrial hydrogenation of unsaturated fatty acids, it's nothing to deal with enzymes or anything like that. It's just a pure chemistry. So, and during that process, a very small amount of this trans fatty acids can form. So basically, trans fatty acids is the unsaturated fatty acid which has a trans double bond. So in this case, I mean, this trans double bond sort of mimics the saturated fatty acid. And everything would have been okay if not for the effects that these trans fatty acids will have in the organism. So, so they are known to actually cause, like, basically, it has been proven already so that they have increased risk for cardiovascular diseases. I mean, basically consumption of too many trans fats. So this is where they came. This is where they come from. So in other words, if you actually cook in a steak, like made from just a pure piece of meat, right? Again, because pure piece of meat is natural, right? So it doesn't have any trans fatty acids to begin with. And when you will be cooking it, I mean, you will not be introducing it because you're not using the same hydrogenation process as what is used at the factory. So then, yes, you may actually come up with some of this peroxy-epoxy compounds which are not good for your health, but you definitely will not come up with the trans fatty acids. So the trans fatty acids in the food come only from the, I mean, basically these oils, I mean, and fats that are used for frying. So, which come from the factory. So if you consume natural, I mean, food coming from the natural sources, no matter what you do with it, you will not introduce this stuff into it. VAXs. So, VAXs are esters of long-chain saturated and unsaturated fatty acids with long-chain alcohol. So at the bottom, basically, I'm just showing you one typical VAX like beeswax. So it's basically like palmitic acid, which is absolutely normal fatty acid, which is esterified to the long alcohol. So basically, you have two long chains of two long hydrocarbon chains, which are basically esterified to each other in the middle. So. And so we know how the VAXs look like. So they're pretty solid, water-repellent substances like the honeycomb, for example. So in the beeswax is a mixture of a large number of lipids, including esters of triacontanol. So that's this long alcohol, so which contains 30 carbons. And the long chain alkane hentiacontane. So basically, Basically, the formula of the beeswax is somewhat similar to this one. Okay, so now we're moving on to the next class of lipids. So again, we still stay on the lipids that contain fatty acids, right? So far we talked only about storage lipids, and here we have only one class, triacylglycerols. So triacylglycerols is just three fatty acids esterified to one glycerol molecule. So they serve only the fuel storage function, and they can be, in plants it's mostly oils, in animals it's mostly fats. So, okay, now we move into the membrane lipids, which are the structural lipids. This is a much more diverse class, actually, as you can see. So the membrane lipids, I mean, they can be divided into phospholipids, glycolipids, and even like the special class of archaebacterial lipids in the membrane. So let's focus first on the phospholipids. Okay, so structural lipids in the membranes, I mean, they are polar. So, and they form so-called double layers. So, which is a central architectural feature of any biological membrane. All the lipids that participate in membrane formation are amphipathic. So this term, amphipathic, means drastically different properties on different ends. So one end is polar or charged, the other end is hydrophobic. So the variability and diversity here in the structural lipids come from different backbones that can be used, from different fatty acids that can be used, and from different head groups that are attached. So of course, I mean, the properties of the head groups determine the surface properties of the membrane. And different organisms have different membrane lipid head groups compositions. And different tissues in the same organism have different lipid head groups compositions. We'll talk about this in detail now. First of all, this is just a very schematic representation of what the membrane lipids look like. So a typical one is a phospholipid. So we have basically a polar head group, and we have two fatty acid tails. We'll talk about chemical composition in the following slide. So these compounds form the so-called lipid bilayer. So the structure in which the head groups look outside, and the hydrophobic tails look sort of inside, inwards. So, and that's what makes it like basically a bilayer. Okay. So the class called glycerophospholipids, I mean, so this is a primary constituents of cellular membranes. So, and they're all derivatives of L-glycerol 3-phosphate. So what is L-glycerol 3-phosphate? Is this molecule here. Nomenclature is very similar to sugars. So, for example, if we remove this phosphate from here, so would it still be L-glycerol or not? No, because then the molecule will be symmetric if we remove this phosphate. It will be, glycerol does not have optical isomers. So, but once we attach this phosphate, so the chiral center is this. Depending on whether the OH looks to the left or to the right, it will be two different molecules. The same nomenclature as with the sugars. Because it looks to the left, it will be left or L-glycerol 3-phosphate. So this is the basis, I mean, for, yes? Glycerol is like, imagine that there will be OH here. So just sort of cover the, I mean, just imagine that you remove this phosphate group, right? But you have CH2OH, so it would be the same as at the top. So, and because, I mean, at this carbon 1 and carbon 3 are already out of consideration because they have two hydrogens, right? They have two same substituents. So you kind of disregard them immediately. So the only carbon that you can consider potential is this carbon number 2. So if it would be glycerol, so it would be CH2OH here and CH2OH here. So these two substituents would be exactly the same, therefore no optical isomers. But once you attach the phosphate, so then this whole part, right? So now you consider CH2O PO3 is different from what is on the top. As a result, it starts to have optical isomers. So basically, in the glycerophospholipids, I mean, only the L isoform is used. Okay, what happens next? So the two fatty acids are usually attached to the remaining two hydroxyls. So the ester linkages with the hydroxyl on the first and second carbons. So this will be called diacylglycerol. So unsaturated fatty acids are commonly found connected to the second carbon, and the saturated ones connected to the carbon 1. So in other words, the two fatty acids that are used for formation of the glycerophospholipids, right? So they are different. So they're not the same. So the one is usually saturated, and the other one is unsaturated. The one which is connected to the second atom, again, if we go back here, second one is this in the middle, to this OH. So the one which connects to this middle carbon is the one which is unsaturated. And the one which is connected to the terminal hydroxyl is the one which is saturated. So different head groups are attached to the phosphate. So phosphate by itself, I mean, is charged, but the modification, I mean, is not, I mean, it's more sophisticated. So this X group, which is attached to the phosphate here, can be different things. So if it's only basically if nothing is attached, so then what we have here would be called phosphatidic acid. So if we remove the phosphate, it would be called diacylglycerol, similar to triacylglycerol, right? But they would be just acylated at two positions. Okay. So these are the most common head groups: ethanol, amine, choline, serine, like it can be even glycerol, or even like more sophisticated ones like sugars. So as you can see, most of them are charged or are polar. For example, ethanol, amine, or choline, so they carry the positive charge at the terminus. The net charge is when you actually combine it with the negative charge of the phosphate group, so it turns to 0. But the group by itself is charged. So, okay. One of the most common components of the plasma membranes is the phosphatidylcholine. So most abundant phospholipid in eukaryotic cells. So many prokaryotes, including E. coli, cannot synthesize this lipid, so their membranes do not contain phosphatidylcholine. So again, this one is in eukaryotes, that is us. So this is how it looks like. Again, it's very similar to this diagram on this slide, except for that we've drawn what the X is. So phosphatidylcholine. So positively charged at the end, but this positive charge is sort of negated by the negative charge on the phosphate group. Okay, so the next group of structural membrane lipids are sphingolipids. So the backbone of sphingolipids is not a glycerol. So instead it's the long chain amino alcohol called sphingosine. So it's shown here at the top. So conceptually, it's just, I mean, this backbone is slightly different from the phospholipid, from the regular glycerophospholipids, but then the X groups are pretty much similar. So the similar X groups can be, or head groups can be attached to the at the top of such basically lipid. An important thing is that the fatty acid is joined to sphingosine via amide linkage, not via ester linkage. See, there is an amino, an HCO. It's like a peptide bond, basically. So it's much more stable than these ester linkages, which we see in the case of the regular glycerophospholipids. So a polar head group is connected to sphingosine by a glycosidic or phosphodiester linkage. So very similar to the previous class. Okay. Perhaps one of the most sort of common examples of sphingolipids would be sphingomyelin. So structurally similar to phosphatidylcholine. So and it contains, I mean, this basically backbone called ceramide and phosphatidylcholine attached to the alcohol here as a polar head group. So sphingomyelin is abundant in myelin sheath that surrounds some nerve cells in animals. So it's because of these lipids, our nerves can actually pass the impulses much faster than in the many invertebrates. So I don't know if you took physiology courses or something, but for those who took, actually, you probably remember that, like basically this surrounding of the axons of the peripheral nerve cells with these special layers of sphingomyelin is important to accelerate the speed of signal transduction. Okay, so we talked about glycerophospholipids as the most abundant class of the structural lipids in the cellular membranes. Sphingolipids, right? And now glycosphingolipids, which basically are important from the point of view of blood groups. So the blood groups are determined in part by the type of sugars located on the head groups of glycosphingolipids. So glycosphingolipids means that, again, if we go back to the formula, is that this bottom part is the same, right? It's just, instead of phosphocholine here, we would have a sugar or oligosaccharide attached. And basically, structure of particular sugar is determined by expression of specific glycosyl transferases. So glycosyl transferases are enzymes that attach a particular sugar to a particular sphingolipid. So individuals with no active glycosyl transferase will have the so-called O group or group 1. So in this case, that is the schematic structure of these glycosphingolipids on the surface of their blood cells. So if the N-acetylgalactosamine is transferred, see, this one is N-acetylgalactosamine, then it will be second group. So, and if basically you have galactose instead of galactosamine, so that would be group 3. And if both of them would be active, so that would be group 4. Okay. So in the last class of the structural lipids, structural membrane lipids are sterols. Sterols are structural lipids found in membranes of most eukaryotic cells. And the key thing here is that the bacteria do not have them. So sterols, the name comes from the so-called steroid nucleus. So these are 4 fused rings, altogether called cyclopentane perhydrophenantrin. So if you want to impress someone with knowing organic chemistry, you can just memorize this name. So probably you've seen it many, many times in different textbooks on different subjects because, these steroid hormones are, relevant to, physiology, organic chemistry, like biochemistry and many other disciplines that you probably studied already and will study. So anyhow, these 4 fused rings together, when they are fully saturated, is called cyclopentane perhydrophenantrin. So in the case of cholesterol, so the hydroxyl group in the A ring is attached, to this position. So there is a hydroxyl group. Hydroxyl group is not charged, but it's polar. So, and there is a very relatively short, basically tail, hydrophobic tail on the other side of the molecule. So this molecule is called cholesterol, so which is the main representative of the class of sterols. So cholesterol serves as a precursor for synthesis of steroid hormones. Also, it's a component of bile acids, and it's also an important component of the membrane, as we mentioned here. But again, so cholesterol is an important component of the membrane only in eukaryotes. Bacteria do not have it. Okay, so here just once again, what are physiological roles of sterol? So we will talk about this in more detail next time. So, but the sterols, especially cholesterol, modulate the fluidity and permeability of the membranes in eukaryotic cell. So thicken the plasma membrane. So mammals obtain cholesterol from food or synthesize it de novo in the liver. Cholesterol bound to proteins is transported to tissues via blood vessels. So, and cholesterol and low density lipoproteins tend to deposit and clog arteries. So you probably all heard, on mass media and everywhere, so about the bad effects, unwanted effects of having high cholesterol. So what's important actually is to understand is which cholesterol we are talking about. So there is low-density lipoproteins, I mean, this is a bad cholesterol, and there is high-density lipoproteins, that's so-called good cholesterol. So in reality, without cholesterol, we will kick the bucket much sooner than with its abundance. So, because, I mean, it's a very important molecule in physiology, of not only human, any animal. Being a precursor of many different hormones and also being an important component of the plasma membranes, we simply cannot live without it. What's important to understand is this. I mean, I intentionally highlighted it so that the cholesterol comes from food and also it can be synthesized inside us. So this is very important because some people just have actually very active synthesis of cholesterol going on. It's pure genetics. It's just what you inherited. So, and regardless what you will do, I mean, like you can eat salad leaves, I mean, 365 days a year, and no meat, no nothing. So, and still cholesterol levels can be skyrocketing. So, again, this is purely because of the internal production. So, and the other, I mean, on the other hand, I mean, so there could be a person whose internal production is very low, so he can, I don't know, eat pure cholesterol with a spoon, and his levels would be below normal or within the normal. So that is what important to keep in mind, right? So it's not only like, not just stupidly say, oh, cholesterol is bad, I mean, so like you need to watch it out. So no, it's better to just be educated in this area. Okay, steroid hormones. So steroids are oxidized derivatives of sterols. So steroids have the sterol nucleus but lack the alkyl side chain found in cholesterol. And they are more polar than cholesterol because of the substituents, as we will see. So steroid hormones are synthesized from cholesterol in gonads and adrenal glands. They are carried through the body to the bloodstream and usually attached to the carrier proteins. So many of the steroid hormones are male and female sex hormones. So here I'm just showing you like just some examples. Of course, I'm not expecting you to memorize it. It's mainly for your reference. So let's just quickly go back a couple slides just to look at the cholesterol once again, right? So we see only one hydroxyl group. This, our favorite cyclopentane perhydrophenanthrene ring, and the hydrophobic side chain, or we could call it a tail. And now, if we go back to the steroid hormones, we will see that there are almost no tails except for this one, but even in that case, it has a bunch of OHs attached, right? So it's generally much more polar compounds. I mean, so they have oxygens attached, I mean, at different positions. So that allows them to easily be transported through the blood, so in the bloodstream. So they're soluble. So actually, they kind of very unique molecules. So on one hand, I mean, so they're soluble enough to be transported like in the regular, like in the bloodstream. But on the other hand, they're hydrophobic enough to pass through the membrane. So they actually, so as a result, most of the steroid hormone receptors are not located on the membrane of the cell, but inside, actually inside the nucleus. So the steroid hormones, the plasma membrane is not an obstacle for the steroid hormones because they can easily pass it. Okay, so and finally we go to the we get to the to talk about biologically active lipids. So this is a very diverse group, and this basically comprises structural and chemically very different compounds. So present in much smaller amounts in storage of structural lipids. So and play vital roles as signaling molecules between nearby cells. Okay. Again, this part of the lecture, I just bring some examples, right? So it's not all of them. It's just, I mean, some of the most important biologically active molecules which we can sort of classify as lipids. For example, arachidonic acid. So arachidonic acid, we had it in this table over here. It was the one which contained 20 carbon atoms and 4 non-conjugated double bonds. Here you go, this one. No, I'm sorry, 24 carbon atoms and 20:4, and the positions of double bonds at 5, 8, 11, etc. So basically, this is the poly, unsaturated, fatty acid, which has actually 4 double bonds in its backbone. Okay, but this acid interesting not as a component of fats or oils or membrane. It's more interesting as a precursor in synthesis of biologically active molecules called prostaglandins. So also thromboxanes and leukotrienes. So these molecules, they all together actually mediate lots of different functions in organisms, such as inflammation, or formation of the blood clots, or even contraction of the smooth muscles. So, and the basically compounds such as aspirin or Tylenol or ibuprofen, so they inhibit the synthesis of these compounds in the target tissues, and that's how the actual effect is reached of this. At the same time, for example, aspirin. So many people have problems taking aspirin because it irritates, the lining of the stomach. And the reason why that's happening is because, it inhibits the same enzyme synthesizing this prostaglandin. In the case of stomach, it's prostaglandin A2 that is being, whose synthesis is being inhibited by the aspirin. As a result, that causes the basically irritation of the stomach lining and like unwanted effects. So the aspirin still does its, reaches its effect in the target tissue, but not in the point of entry. Vitamin A, so, or retinol, so visual pigment of vertebrate eye. So basically vitamin A, it's a half of the molecule of beta carotene. So do you know where you can find this beta carotene? Huh? Carrots, exactly. So, and why these carrots are usually served with the dip? Well, because it's tasty. That's a good reason, right? But also, what is good is because beta carotene is not water soluble and it's more lipid soluble. So it's actually better to have it with like a sour cream or this dip, which is kind of a bunch of lipids together. So you will get at least some of it. So the carrots are good, especially in this time of the year when there is not, sun is not every day, so we actually just to have this visual pigment supply. So retinol, basically, what happens in the eye? So this molecule of retinol turns into retinal, so it's being reduced, and then the retinal, it's the one which is attached to the protein opsin. And it basically undergoes this conversion from the cis to the fully trans version, and that's actually when the photon or the quantum of light is being sensed. So this is basically the reaction of chemical basis of human vision, sort of. This reaction. Another interesting molecule is a vitamin D. So, and here you can also kind of recognize the cholesterol traits. So, not surprisingly, because it belongs to the same class. So this 7-dehydrocholesterol, is being actually through a number of steps in synthesis turns into the cholecalciferol in vitamin D3, and basically then it can be isomerized to the to this dehydroxyvitamin D3, which is an active form. So what's interesting here is that this vitamin can be synthesized in the human skin at the sun. So if you're exposed to the UV light, moderately, of course, so the good amounts of this vitamin D3 would be synthesized internally. So another lipid-soluble vitamins such as E and K, which serve antioxidant function in the body. So we're not going to be actually talking much about them. You can see that they're clearly lipids because they have these heads and the long, basically hydrophobic tail. Okay, so let's just summarize what we talked about. So lipids are a very diverse class of molecules. So let's focus on the most important ones. So the most important ones are the ones which are used for energy storage, and here we have only triacylglycerols. So triacylglycerols are very simple, chemically very simple molecules such as glycerol is esterified to 3 fatty acids, usually the same in this case. Depending whether the fatty acids will have double bonds or not, so the resulting compounds will be either liquid or solid. So if they're solids, they're called fats. If they're liquids, they're called oils. Okay, so another class of lipids basically are the structural. I mean, it's like a big class. I mean, first was the energy storage, and the second one is structural lipids. So structural means that they form the membrane structures. So here we have glycerophospholipids, sphingolipids, and we have steroids. So the main component, cholesterol, which is a very important component in the cellular membranes. So, and finally, we were talking about the biologically active molecules, which are present in uncomparably small amounts, I mean, than the first two classes, but still are very important for the physiology of the living organisms. Okay, that's it for today.